Hello, my name is Aaron Jacob and I'm going to explain my science project. Now, the topics I cover include Hermite polynomials like your polynomials, moment of inertia and the inertia matrix, and finally, the use of Hamiltonian and Lagrangian mechanics in rocket dynamics. Now, let's begin with Hermite polynomials. In mathematics, Hermite polynomials are a classic orthogonal polynomial sequence. These polynomials find uses in a lot of areas, including probability, combinatorics, numerical analysis, quantum physics, and systems theory. These polynomials were defined by Laplace in 1810, although he didn't get any credit for it, and these polynomials were finally named after Charles Hermite, who wrote about them in 1864. Now, let's look at how we can define Hermite polynomials. There are two main definitions of Hermite polynomials. The first, commonly known as a probabilist definition, is given as follows. Hen of x is equal to minus 1 whole raised to n into e raised to x squared by 2 times the nth differential of e raised to minus x squared by 2 with respect to x, which can also be equated to x minus d by dx whole raised to n times 1. The other definition is the physicist definition, which is practically the same as the probabilist definition, with some subtle differences. Now, here I have listed the first few Hermite polynomials, both for the probabilist version and the physicist version. We can see that they start out with the same value, as in the probabilist version and the physicist version, but for n is equal to 0, both of them are equal to 1. And then we see that as n increases, their values keep changing. Now here we have a graph of the first few polynomials. Now one might notice that for the graph of each of these polynomials there is a certain symmetry to it, either any one of the axes. Now let's look at a few properties of Hermite polynomials. The very first property we come across is the symmetry condition, which states that the nth Hermite polynomial of minus x is equal to minus 1 whole raised to n into the nth Hermite polynomial of x. Now, the second property. We obey the recurrence relations given below. The n plus 1th Hermite polynomial of x is equal to x times the nth Hermite polynomial of x minus the differential of the nth Hermite polynomial of x. Now, as you can see, the first recurrence relation was for the probabilist version of the Hermite polynomial, and there is a similar recurrence relation which the physicist version of the Hermite polynomial satisfies. Now, the third property. The Hermite polynomials obey the sum given below. Sigma from k is equal to 0 to n of minus 1 raised to n minus k into nck times the nth Hermite polynomial of k is equal to 2 raised to n into n factorial. The next property. Now, the Hermite polynomials are orthogonal with respect to the weight function given by omega of x is equal to e raised to minus x squared by 2, or omega of x is equal to minus e raised to x squared. Thus, we have integral from negative infinity to infinity of the mth Hermite polynomial of x times the nth Hermite polynomial of x times the weight function is equal to 0, where m is not equal to n, and we get the following two results. Moving on to the final property of Hermite polynomials. Now, the probabilist Hermite polynomials are solutions of the differential equation given here. Now, rewriting the differential equation as an eigenvalue problem gives us L of u is equal to u double dash minus x u dash is equal to minus lambda of u. And the solutions for this equation are the eigenfunctions of the differential operator L. Now, this eigenvalue problem is called the Hermite equation, although the term is also used for the closely related equation u double dash minus 2x u dash is equal to minus 2 lambda u, whose solutions are the physicist's Hermite polynomials. Next, let's see how Hermite polynomials are related to Laguerre polynomials. We have two equations which relate Hermite polynomials to Laguerre polynomials. The first equation is the 2n plus 1th Hermite polynomial of x is equal to 2 times minus 4 raised to n into n factorial into x into root of the nth Laguerre polynomial of x square. Similarly, we have another equation for the 2nth Hermite polynomial of x. Moving on to Laguerre polynomials. Let's begin with Laguerre polynomials. Now, Laguerre polynomials are named after Edmond Laguerre, and they are the solutions of Laguerre's equation, which are given as xy double dash plus 1 minus x into y dash plus ny is equal to 0. More generally, they are the solutions of xy double dash plus alpha plus 1 minus x into y dash plus ny is equal to 0. The upper equation is just a special case where alpha is equal to 0. Now, Laguerre polynomials arise in many different situations, such as quantum mechanics, especially in the radial part of the solution of the Schrödinger equation of the one electron atom. They also find uses in describing the state Wigner functions of oscillator systems and also in the Morse potential of quantum mechanics and also in 3D isotropic harmonic oscillators. Moving on, let's look at how we can define Laguerre polynomials. We can define Laguerre polynomials using Rodriguez's formula, which is given as the nth Laguerre polynomial of x is equal to e raised to x upon n factorial into the nth differential of e raised to minus x into x raised to n with respect to x. One can also define these polynomials using the recurrence relation given as follows. The k plus 1th Laguerre polynomial of x is equal to 2k plus 1 minus x into the kth Laguerre polynomial of x minus k into the k minus 1th Laguerre polynomial of x, the whole divided by k plus 1. Of course, we have to define the first two terms in the series, which is the 0th and the first Laguerre polynomials of x, which are respectively 1 and 1 minus x. Let's move on to the first few polynomials of Laguerre, which are listed in this table. We see that for n is equal to 0, the Laguerre polynomial of x is 1, and for n is equal to 1, it is minus x plus 1, and so on. Now listed here is the graph of the first few Laguerre polynomials. Now we come to the closed form of Laguerre polynomials, which is given as the summation from k is equal to 0 to n of nck into minus 1 whole raised to k into x raised to k whole divided by k factorial. The generating function for these comes out as follows. Sigma from n to infinity of t raised to n into the nth Laguerre polynomial of x, which is equal to 1 upon 1 minus t into e raised to negative tx upon 1 minus t. Now we will look at generalized Laguerre polynomials. For any arbitrary real alpha, the polynomial solutions of the differential equation given here, which is xy double dash plus alpha plus 1 minus x into y dash plus ny is equal to 0, are called generalized Laguerre polynomials, which we saw previously in the definition of Laguerre polynomials. They can also be defined recursively, just as before, as the k plus 1th Laguerre polynomial of x becomes 2k plus 1 plus alpha minus x into kth Laguerre polynomial of x minus k plus alpha into k minus 1th Laguerre polynomial of x upon k plus 1. Having defined the first two terms in the series, that is for n is equal to 0 and n is equal to 1. The simple Laguerre polynomials we saw up till now arise when alpha is equal to 0 in the generalized polynomial sequence. Now let's look at some properties of Laguerre polynomials. The very first property we come across is orthogonality. Now we see that the generalized Laguerre polynomials are orthogonal from 0 to infinity with respect to the weighting function x alpha e raised to minus x, and that leads to the result given here, that is integral. The second property we come across for Laguerre polynomials are two multiplication theorems which were given by Erdely, and now these theorems are listed below. Let's look at the next property, that is the derivatives of Laguerre polynomials, which states that any kth differential of the nth Laguerre polynomial of x with respect to x is equal to minus 1 raised to k times n minus kth Laguerre polynomial of x with respect to alpha plus k if k is less than or equal to n. Otherwise, it is 0. These polynomials also satisfy the following two relations, that is n plus 1 into n plus 1th Laguerre polynomial of x is equal to 2n plus 1 minus x into nth Laguerre polynomial of x minus n times n minus 1th Laguerre polynomial of x. They also satisfy x times the differential of nth Laguerre polynomial of x is equal to n times nth Laguerre polynomial of x minus n times n minus 1th Laguerre polynomial of x. Let's see how they are related to Hermite polynomials. We see that there are two equations which relate Hermite polynomials to Laguerre polynomials, just as we saw in the case of Hermite polynomials. We see that the 2nth Hermite polynomial of x is equal to minus 1 whole raised to n times 2 raised to 2n into n factorial into negative square root of the nth Laguerre polynomial of x square. As a result of these two equations, generalized Laguerre polynomials can also be used in the treatment of the quantum harmonic oscillator. Let's move on to the moment of inertia and inertia matrix. Let's begin with the moment of inertia and the inertia matrix. Moment of inertia is the rotational analog to mass. That is, the mass moment of inertia about a fixed axis is the property of a body that measures the body's resistance to rotational acceleration. The greater its value, the greater the moment required to provide a given acceleration about a fixed period. And of course, one necessary condition is that the moment of inertia must be specified with respect to a chosen axis of rotation. Moving on, we'll look at the formula for moment of inertia. Given an object of mass m and effective radius k, which is known as the radius of gyration, we can define for an axis through its center of mass the moment of inertia as mk square. With respect to a solid body with density rho, the moment of inertia is defined by the volume integral, which is given as the integral of rho of r into r square into dv, where r square is the perpendicular distance from the axis of rotation. This of course can be broken into components as shown in the formula. The formula specifies the moment of inertia along the jk axis, and we can similarly calculate for other axes as well. How is moment of inertia related to angular momentum? Angular momentum is equal to moment of inertia times omega, where omega is the angular velocity vector. Now we will come to the inertia matrix and its components. Let's start with the components. Commonly, the symbols Ixx, Iyy, and Izz are used to express the moments of inertia of a 3D rigid body about its three axes, where Ixx is equal to integral of y square plus z square times dm, which is mkx square, where kx is the radius of gyration around x-axis, and similarly for Iyy and Izz. Now the products of inertia are given by Ixy, Ixz, and Iyz, where Ixy is equal to integral xy dm, Ixz is equal to integral xz dm, and Iyz is equal to integral yz dm. Let's move on to the final inertia matrix. The final inertia matrix is given as follows: Ixx minus Ixy minus Ixz is the first row, minus ixy, iyy, I minus yz is the second row, and finally the last row, minus ixz, minus iyz, and izz. This entire matrix can be used to describe the moment of inertia of a rigid body about any arbitrary 3D axis. Another way to see this formula is by expanding it, that is, for using the density of the rigid body, we obtain moment of inertia is equal to integral of rho of xyz times the inertia matrix expanded times dx dy dz. Now let's move on to the final topic, that is Lagrangian and Hamiltonian rocket dynamics. Now let's begin with Hamiltonian and Lagrangian mechanics in rocket dynamics. We will be using this diagram as a reference. This diagram describes the motion of the rocket along a rotating straight line. Now, consider the rocket as a point of variable mass moving with velocity xi. The differential equation of the rocket motion can come up as m double differential of the position variable is equal to m dot ci plus fi for I is equal to 1, 2 or 3. Now we have t is equal to the time, and m of t is equal to mass at time t, and we have m dot is equal to d m by dt, that is the rate of the burning of the fuel. We have xi of t is equal to the Cartesian coordinates of the rocket in fixed coordinate system at the instant t. We also have ci is equal to velocity of the expelled mass relative to the rocket, and we have fi, that is the applied force. Usually fi is the sum of aerodynamic and gravitational forces. Now to the equation mxi double dot is equal to m dot ci plus fi. We add m dot xi dot. This can be simplified to dy dt of mxi dot, which is equal to m dot ui plus fi, where ui is equal to xi dot plus ci, where ui is the absolute velocity of the expelled mass in fixed coordinate system. Now we introduce generalized coordinates q alpha by the set of equations given by xi is equal to psi of q alpha comma t for I is equal to 1 to 3 and alpha is equal to 1 to n, where n is equal to 1, 2 or 3 depending upon the degrees of freedom of the rocket. If n is equal to 1, the rocket is constrained to move along a curve. If n is equal to 2, then the rocket is constrained to move along a surface. If n is equal to 3, then the rocket is free to move about in any direction. Now, the kinetic energy of the rocket at any point of time t can be given by Ke is equal to 1 by 2 m of t into xi dot to xi dot. Now, differentiating the equation, which is dy dt of mxi dot is equal to m dot ui plus fi. If we differentiate this by dou xi upon dou q alpha, we get the following equation, that is dy dt of mxi dot dou xi dou q alpha equal to m dot ui dou xi dou q alpha plus fi into dou xi on dou q alpha. Now we can easily verify that the left hand side of the equation can be expressed in the form d by dt of dou t upon dou q alpha dot minus dou t upon dou q alpha, where t is equal to the kinetic energy of the rocket. Hence we can write the equation in the following form: d by dt of dou t upon dou q alpha dot minus dou t upon dou q alpha is equal to m dot ui dou xi upon dou q alpha plus fi dou xi upon dou q alpha. Now this equation is the Lagrangian form of the rocket equation in generalized coordinates. By integrating this equation twice, the position of the rocket at any time t can be found out. Now, let theta be the angle that the straight line makes with the vertical in the reference diagram that we are using. Let me just draw the diagram again. This is the vertical axis, and if this is the rocket of mass m, this is the angle theta. Therefore, we get the coordinates x1, x2 and x3 as r sine theta cos omega t, x2 is r sine theta sine omega t, and x3 is r cos theta, where r is the distance from the apex, which is this point. Now theta and omega are constant, and xi is equal to xi of rt, where q1 is equal to r, n is equal to 1, and thus the Lagrangian equation that we obtained will get the form dy dt dou t upon dou r dot minus dou t upon dou r equal to m dot ci plus xi dot into dou xi upon dou r plus fi dou xi upon dou r. Let me write that a little better. Is equal to m dot ci plus xi dot dou xi upon dou r plus dou xi upon dou r. Now the rocket is subject to uniform gravitational force mgi, which will be oriented downwards, that is along the x3 axis, and we can define the gravitational force gi, that is the acceleration of gravity, as 0 0 minus g, and the force on it as 0 0 minus mg, since the force is along the x3 axis. Now, suppose the relative velocity of expelled mass is ci, which we have defined before, where the vector ci is of constant magnitude c and is oriented along a rotating straight line towards the apex O. That we get ci is equal to minus c into xi upon r. Thus, we modify the kinetic energy equation of the rocket, which becomes half m xi dot is equal to half m r dot square plus omega square r square sine square theta. Now, from the Lagrangian equation that we arrived at, we get d by dt of dou t dou r dot minus dou t upon dou r. Now, in this, the left hand side of the equation, we have this part is equal to m dot r dot plus mr, and dou t by dou r can be written as n omega square sine square theta times r. On the right hand side of the equation, which is m dot ci plus xi dot dou xi by dou r plus fi dou xi upon dou r. Now this part of the equation becomes minus m dot c plus m dot r dot, and this part becomes minus mg cos theta. And so we finally arrive at the Lagrangian equation of the rocket motion, which is mr double dot minus m omega square sine square theta times r is equal to minus m dot c minus mg cos theta. This is the Lagrangian equation of rocket motion. Now we will arrive at the same equation using the Hamiltonian method. Now let's begin with the Hamiltonian method for rocket dynamics. Now remember, we defined the equation xi is equal to xfi q alpha comma t for I is equal to 1 to 3 and alpha is equal to 1 to n. Now if this equation contains time explicitly, then the kinetic energy, which is T, becomes 1 by 2 m into dou xi upon dou q alpha into q alpha dot plus dou xi upon dou t into dou xi upon dou q beta into q beta dot plus dou xi upon dou t, which becomes 1 by 2 n dou xi upon dou q alpha into dou xi upon dou q beta into q alpha dot into q beta dot plus m times dou xi upon dou q alpha dou xi upon dou t into q alpha dot plus 1 by 2 n dou xi upon dou t into dou xi upon dou t. This entire equation can be abbreviated as d of t comma q dot. Now we define a new dynamic variable, that is p alpha, where p is t of t q dot upon del q alpha dot, which is m dxi del q alpha times del xi upon del q beta into q beta dot plus m del xi upon del q alpha times del xi upon del t. Now consider the function h t q dot, which is q alpha dot times del t q dot upon del q alpha dot minus t q dot, which can also be written as h t q dot is equal to q dot alpha P alpha minus dt q q dot. From this we arrive at del h dq q dot is equal to q dot alpha del p alpha plus p alpha del q alpha dot minus del t upon dou q alpha into del q alpha plus dou t upon dou q alpha dot into del q alpha dot, which can be written as q alpha dot del p alpha minus dou t upon dou q alpha into del q alpha. Taking another variation of HTQP, we obtain del H of TQP is equal to dou H TQP upon dou Q alpha plus dou H TQP upon dou P alpha into del P alpha. Since del Q alpha and del P alpha are independent, and also since del H TQP is equivalent to del H TQ dot, we can say that Q alpha dot is equal to DH TQP upon del P alpha, and also that minus of dt tq q dot upon del q alpha is equal to del h tq p upon del q alpha. Now we will substitute the above result in Lagrange's equation, which will give us P alpha is equal to minus dou h tq p upon dou q alpha plus m dot ui del xi upon del q alpha plus fi del xi upon del q alpha. Thus we have arrived at the generalized Hamiltonian equations for rocket mechanics, which are P alpha is equal to minus dou h tq p upon dou q alpha plus m dot ui dou xi upon dou q alpha plus fi dou xi upon dou q alpha, and q alpha dot is equal to dou h tq p upon dou p alpha. These two equations are the generalized Hamiltonian equations for rocket mechanics. Now consider a potential function v of q t such that m dot ui dou xi upon dou q alpha plus fi dou xi upon dou q alpha is equal to minus dou v qt is equal to minus dou v qt upon dou q alpha. Thus we can get a new form for q alpha dot, which is dou by dou p alpha of h tqp plus v qt, and we get another form for p alpha, that is minus dou by dou p dou minus dou by dou q alpha of HTQP plus VQT. Now the Hamiltonian is defined as sum of HTQP and the potential function. Now we will apply the Hamiltonian method to the example of rocket motion along the rotating straight line, which was solved previously using the Lagrangian method. We have the kinetic energy according to q dot, which is 1 by 2 m into r dot square plus omega square r square sine square theta. We have p is equal to dou t q dot upon dou q dot, which is equal to mr dot. We also have r dot is equal to p by m. Using r dot is equal to p by m, we get t of tqp is equal to 1 by 2 m into p square upon m square plus omega square r square sine square theta. Now we have p is equal to del h upon minus dou r plus m dot ui plus fi dou xi upon dou r, which is equal to m omega square sine square theta times r minus m dot c plus m dot r dot minus mg cos theta. After simplification, we will arrive at mr dot double dot minus m omega square sine square theta times r is equal to minus m dot c minus mg cos theta, which is the same result that we got using the Lagrangian method.